One of the many things we've learned by living and working on the space station for months at a time is that more than half of the astronauts have returned to Earth with vision changes. A new investigation is learning how spaceflight and something called fluid shifts affects vision and eye shape. Lori Meggs is at the Payload Operations Integration Center at NASA's Marshall Space Flight Center with more. Lori?
Have you ever had the blood rush to your head? Well, crew members have that same feeling once they arrive at the space station. Much is the same for folks who are suffering from swelling in the brain or confined to bed rest. That's because all of the fluid tends to shift up. Well, now a new investigation is looking at whether these fluid shifts are causing vision problems for astronauts when they return to Earth. Results from this study could help them to develop countermeasures for folks here on Earth as well as the astronauts with vision damage. I had the opportunity to visit the lab where the crew members undergo testing for this investigation before they fly to space station. We're talking fluid shifts. Mike Stenger is here. We're in the cardiovascular lab at Johnson Space Center. Mike, fluid shifts, I mean, is that what we really think it is? How your fluids are moving around your body?
It's pretty much what it sounds like. We're investigating the impact of the headward fluid shift that's caused by spaceflight on this ocular syndrome, this visual impairment and intracranial pressure syndrome. One of the primary hypotheses is that you get this headward fluid shift and that the subsequent results of that fluid shift are causing an elevation in intracranial pressure, which is causing swelling of the back of the eyeball, which is affecting vision.
So when the crew members come back, they've been having some vision problems, and that's a really big thing for the space station program right now, is to figure out why this is happening.
Right. So one of the hypotheses is that it's intracranial pressure. No one's actually investigated this. So this is the first experiment to look at the blood flow going up into the head. It's a very comprehensive experiment where we're looking at all the blood flow pathways into the brain, what fluid is doing in the brain, how it's filtering out of the blood vessels, going into cells, into the interstitial spaces. We're also investigating how the human body changes its venous drainage strategies, because there's no gravity pulling the blood back to your heart. One of the hypotheses is that venous congestion is causing this VIP syndrome. And so we're looking at the various drainage pathways out of the head as well.
All right, can I see how it might all work here when you test the subjects?
Absolutely.
All right. So I feel like a test subject now, Mike. Now what's happening?
So right now you're getting bilateral ultrasound scans. David is scanning your carotid jugular vein, and Tim over here is scanning your carotid artery. So on one side we're imaging the blood going into your head, and on the other side we're imaging the blood draining out of your head. So right now you're laying flat on your back, and so we want to investigate everyone's individual strategy for how they manage this blood flow. So I'm going to tilt your head down to 15 degrees.
Okay.
You ready?
Yes.
So there, that's 15 degrees head down. Wow. And we would measure blood going into your head at this angle, and then
yeah, it's definitely going there.
It's definitely going there, and David will see the jugular vein in your neck engorge as it starts to back up a little bit. And during a natural experiment, we'd have a third sonographer scanning your eyeball right now, and looking at the blood flowing in and out of your eye as well as in your brain. We would have you in this posture for about 30 minutes.
Oh my.
Yes. So we're getting a time course of changes as well. And we have other modalities that we'd like to show you as well. So we'd be taking pictures of the back of your eye right now to see how the choroid, the vascular network in the back of your eye, how it swells or how it doesn't swell, changes in the nerve fiber layer in the back of your eye. We also measure eye pressure using a rebound tonometer. And we also have some non-invasive measures of intracranial pressure that we can show you as well that we would be measuring at this time. We think that different astronauts respond differently to the headward fluid shift, which is why some astronauts develop more severe symptoms of VIP and others do not.
So how many are going through this process that I'm going through right now?
We're going to investigate 10 astronauts. So far, we've already done pre-flight data collection on 3 of them. So our first 2 in-flight astronauts are the 2 one-year crew members.
So what's he doing now, Mike?
So this is a Spectralis OCT camera, optical coherence tomography. You probably had this done at your annual eye exam, but you'd be sitting upright with your face in a chin rest and your forehead pressed against the forehead rest. He's taking really detailed pictures of the back of your eye. And this is a camera that we have on station right now. So they have it up on station now. They have the chin rest. This particular device is unique in that we have a one-of-a-kind boom arm that allows him to orient the camera in such a position that he can get these images while you're laying on your back. And you can also do it while you're laying head down. So while you're head down and while you have that rush of fluid to your head, we can see how the fluid engorgement in the back of the eye, it's called the choroid, how that's different in different astronauts. So we think that the different response to that headward fluid shift may predict the severity of VIP.
And who gets it?
Who gets it and who doesn't, yes. One of the interventions that we're interested in is lower body negative pressure to reverse the headward effects of these fluid shifts in spaceflight. So we will move a lot of our hardware from the US segment over to the Russian segment, including the OCT. But the base is too big to transport, so we're going to free float the camera. The astronaut would just hold it in front of their face while another astronaut runs the computer to take pictures of the back of the eye while we're trying to pull the fluid back out of your head. So we also think that some astronauts will respond better to the LBMP intervention than others.
Uh-oh, he has something else.
So he's got a rebound tonometer. It's called an eye care tonometer, and this measures the pressure in your eye. So there's the difference between the pressure in your brain and the pressure in your eyes is called the translaminar pressure gradient. That affects the severity of the symptoms we think you get. So he has to come in here to do this. It doesn't hurt. You won't feel a thing.
So
I've heard that before.
This little probe right here is going to bounce off the front of your eye, and it's going to measure the pressure. Okay, so you can just stare straight at it. Go ahead and blink for me. And then open your eyes, nice and wide and open.
He just performed 7 measures. That was uncomfortable at all, or?
No, not really. Just, when you have something pointing at your eye. It's a little...
So that's also, we call that a non-invasive measure of intraocular pressure.
Yeah. And so we would do that 3 or 4 times at all of the different positions.
All right, I'm good with 1, though. That's good. Thank you. Thanks. So that's it, as far as that's it. But
that's in a nutshell, really.
All right. I like it here. I'm going to stay a second out.
All right. Enjoy yourself.
Oh, that was fun. Thanks to the team there for letting us on the inside here at the Payload Operations Integration Center. They're assisting with that final fluid shifts experiment for the first round for the crew member, the final crew member undergoing that this morning. Today, Jimmy Whitaker is the Payload Operations Director leading the team here, assisted by Stephanie Dudley. And then the PACOMs are Chrissy Stinson, Crystal Morgan, and Cody Jones. That team there all working hard and working with our astronauts to accomplish all of these fine experiments.